Delaware Tech, Chemistry 100, Chemistry 110, Acids and Bases, Introduction. Acids and to a lesser extent bases have been known for thousands of years. In fact, the word acid comes from an ancient Latin word, acidus, which means sour because many food acids actually have that sour taste. Just think about lemon juice. And a number of chemists have actually looked at the chemical nature of acids since the late 1700s, including the famous French chemist Antoine Lavoisier, who I've talked about before. Well, in 1884, the Swedish chemist Svante Arrhenius gave a new definition to acids, which really revealed their true chemical nature. And what he said was that acids are molecules that release hydrogen ions, H plus ions. Now remember, an H plus ion is a hydrogen atom that has been stripped of its only electron, leaving behind the H plus, which is really just a proton for most hydrogens. So because of that, another way to say this is that an acid is a proton donor. It's a proton releaser. We usually say the phrase proton donor, however. So an example of that would be hydrochloric acid. And you'll notice in this particular chemical equation, I did not write that each component is aqueous, that is dissolved in water. Just assume it's all in water, unless I say otherwise. So we have HCl in the water, and it releases protons, H plus ions, hydrogen ions, and what's left over is the Cl minus, the remaining anion from the acid. Now, I will tell you that H plus ions don't exist by themselves in water, and we'll get to that in a second. He also defined bases as molecules that release hydroxide ions, that is OH minus ions. So compounds that donate hydroxide to the solution, to the water, when they're put in water, when they dissolve in water and break up into their ions, if one of those ions is an OH minus ion, that would be a base according to Arrhenius's definition. So a great example of that would be sodium hydroxide, which when you put it in water will split up into sodium ions, Na+, and OH minus ions, hydroxide ions. So he narrowed these definitions down pretty tightly. Acids have to produce protons, bases have to produce hydroxides. Now, I mentioned that a proton is never truly free when it's released in water. In fact, if there's water present and a hydrogen ion, a proton is released, the hydrogen ion will bind to the water. The water can actually chemically connect to the H+, forming this H3O+ ion, which we call hydronium ion. The IUM ending is your tip-off that it is a positively charged ion. So the more proper way to write the hydrochloric acid reaction that I showed up at the top, what we call the dissociation reaction, because hydrogen chloride, HCl, hydrochloric acid, is dissociating into a proton and a chloride ion. The more proper way would be to say it's really dissociating, it's really interacting with water, and water is picking up that proton. It's acting as what we call a base, but I haven't gotten to that definition just yet. And resulting in a chloride ion, and instead of a free proton, a free H+, we have hydronium ion. So this is the true form of acid when it's put in water. So Arrhenius's definition, unfortunately, was limited to just hydrogen-type acids, which is fine for now, and hydroxide-type bases, which is limiting because there are other types of bases that can do these same types of reaction of picking up protons. So in Arrhenius's definition of acids and bases can interact with each other by a standard double replacement reaction. One releases a proton, one releases a hydroxide. The proton and the hydroxide will come together, as shown over here, and form a water, a covalent molecule. It's no longer an ionic molecule in this case. And that's actually very favorable. In fact, it's so favorable it produces a lot of heat. And this is why it's quite dangerous to mix concentrated acids with concentrated bases, because the amount of heat produced can cause boiling of your mixture and splashing, and it could get on you, and it's quite dangerous in the lab. So you always have to be careful about mixing acids and bases. Now, almost 40 years later, two other scientists working completely independently of one another, Johannes Brønsted from Denmark and Thomas Lowry from England, came up with new definitions of acids and bases. They both liked Arrhenius's definition of acids, so they kept that the same. Acids, as proton donors, they release hydrogen ions, H+ ions, and we have the same example of hydrochloric acid. But they changed the base definition. They made it broader, so it included more types of bases. So their definition says that a base accepts the hydrogen ions. In other words, it's a proton acceptor. So this is directly opposite of what an acid is in their definition. And so we still can include hydroxide examples like sodium hydroxide. And when you put sodium hydroxide in water, it immediately breaks apart into sodium ion and hydroxide ion. And that hydroxide ion is a proton acceptor, so that it will bind to protons, H+ ions, and produce water. We actually saw that in the example that I showed you for an acid-base reaction for Arrhenius acids and bases. But the same can hold where hydroxide is now acting as not only as a hydroxide donor, but also as a proton acceptor. But their definition went one step further and allowed other types of bases, things like nitrogen bases, like ammonia, shown here, NH3. NH3, the nitrogen, has a lone pair of electrons on it that I've shown here. I'm not always going to draw the lone pair of electrons. You have to know they're there. And that lone pair can act as a proton acceptor. It will bind to the proton that might be released in the water or in whatever solvent you have, and will produce ammonium ion, NH4+. So it's ammonia plus an H+, so we add the H, we add the plus, and we get ammonium ion. So the Brønsted-Lowry definition includes both hydroxide type and non-hydroxide type bases. And this was a big change because there were a lot of bases that were known that had no hydroxides on them that needed to be accounted for, and these gentlemen came up with a way of doing that. So these definitely include the hydroxide bases, the alkali metal hydroxides like sodium and potassium hydroxide, but also the alkaline earth hydroxides like magnesium hydroxide, calcium hydroxide, barium hydroxide. But all of these produce hydroxide. But it also includes these nitrogen type bases as well as a lot of other bases. The nitrogen bases include ammonia, shown here, NH3, a derivative of ammonia, an organic compound, methylamine, that's the CH3NH2, another organic compounds being carbon-based compounds. This one, C5H5N, is called pyridine, and the last one shown here, C6H5NH2, is called aniline. And there are many other nitrogen-based bases. There are other more exotic bases, but those are going to be outside of the scope of this course. But in any case, acids and bases can still interact like I showed you before with the Arrhenius acids and bases in a double replacement reaction, where an acid will react with a hydroxide base to produce some kind of salt and water. And that's what you'll always get with a hydroxide base. But it also includes other reactions of other types of bases, these non-hydroxide bases, where you end up with an anion and a cation, which in fact come together to become another salt. So that would actually be ammonium chloride if you were to dry it out, if you got rid of the water. So in that case, it's just a salt. So the the Brønsted-Lowry definitions are the ones we're going to go with for the most part in this course, but it's important to understand the specific Arrhenius bases as well. So the Brønsted-Lowry says the acid is a proton donor, and the base is a proton acceptor. So the acids and bases always come in pairs in any acid-base reaction. For instance, if I have an acid with a base, and I'm representing base as B, and I've shown a lone pair. You don't have to draw the lone pair. And this will result in the proton being transferred from the acid to the base. And you'll notice what's left is this A minus. The A minus is whatever anion the acid was made from. So this is a hypothetical acid HA and a hypothetical base B. And in the end, you end up with just the anion from the acid, and the base has now gotten a proton added. We call this a protonated base. So we start with an acid and a base, and we end up with a new base, what we call the conjugate base. That's the A minus in this case, because theoretically this reaction can go backwards, and A minus can pick up a proton. Therefore, A minus is a proton acceptor if it went in the backwards reaction. So we call it the conjugate base. It's the base made from an acid. And BH plus is the conjugate acid. It's now an acid form that was created from the base. And you'll notice all four of these ions or compounds are dissolved in water, so they're aqueous. So an example of that is the one I just showed you. HCl plus ammonia gives chloride ion, that's the conjugate base of HCl, and ammonium, NH4 plus, which is the conjugate acid of ammonia. And when no specific acid or specific base is actually added to the water can act as a weak base to form, so it can act as a base picking up a proton to form hydronium ion, which is a strong acid, or the water can act as a weak acid giving up its proton to form hydroxide ion, which is a strong base. So water is both a weak base and a weak acid, and depending on whether it acts as a weak base or a weak acid, it will form a strong acid or a strong base. Hydronium ion, which is essentially your protons in water, and hydroxide ion, the strong base that is the base form of water. So let's look at the properties of acids versus bases, and there are a lot of different properties to keep track of. Protons. Well, we know from the definition that acids donate protons. They produce protons, they donate them, whereas bases bind to protons, what we call accept protons. And when you don't have an extra base added to the acid, the water will act as a base, so water will pick up the proton from the acid. HA is our theoretical acid, and the result will be our conjugate base, A minus, plus hydronium ion, which will go up, and the hydronium ion going up is what makes an acid an acid. It's the protons released to form this hydronium ion. Whereas with a base, if you just throw a base in water, water will act like a weak acid. It doesn't do it well, but it will do it enough if there's a strong base. And the base will literally rip a proton off of water, leaving behind hydroxide ion, which is a very strong base. And the base will now be protonated. It will have an extra H plus on it. And now it will be the conjugate acid of the original base. And if we react these together, we can get HA plus our base, making A minus, and our base H plus. We've already seen that. But we can also look specifically at just the hydroxides, in other words, just the Arrhenius type bases, the hydroxide bases, which are metal hydroxides. Me is a general metal here, reacting with some kind of general acid, and you end up making a salt, which is basically salt is what chemists call ionic compounds. So it's an ionic compound composed of the metal ion from the base and the anion from the acid coming together, and what's left is the H plus and the OH minus to form water, which is very favorable and very hot. So an example would be HCl and NaOH. We've already seen this to produce NaCl, our salt in this particular equation, and water. A little more complex one of a hydroxide base would be calcium hydroxide reacting with H2SO4. This is sulfuric acid. In this case, we take the calcium ions from the base and we take the sulfate ions from the acid, and we bring them together to form another ionic compound. Remember, these are double displacement reactions when you have hydroxide bases. So you end up making a new salt, calcium sulfate, and in this case, you have 2 protons and 2 hydroxides, so you end up making 2 waters. So the taste. Well, we know from ancient history that acids taste sour. That's where the word acid comes from. Bases actually taste bitter, and there are a number of different drugs that will actually taste bitter because they have basic groups on them, like those nitrogen bases that I showed you before. Morphine would actually be an example of that, but I don't recommend you tasting morphine to try that out. Touch. Well, what happens when you touch these chemicals with your bare hands, which you clearly should never do? Acids will burn your skin. Bases will burn your skin too, but first they will feel slippery. And you probably don't want to hear why they feel slippery, but the fact is strong bases will literally turn the molecules that make up your skin into soap. So you can actually turn your skin into soap. I do not recommend this, but that is why they feel slippery. If you get, say, concentrated or even dilute sodium hydroxide or potassium hydroxide on your hands, you'll feel that slipperiness. Of course, wash your hands immediately if you touch any of these strong bases or acids, even if they're dilute. Reactivity with metals. Well, we already know from previous experience with chemical reactions that acids react with certain metals. Certain metals like zinc and calcium and magnesium will react with acids like hydrochloric acid, as well as all the other acids, and produce some kind of salt, in this case zinc chloride. These reactions are single replacement reactions. So the zinc is replacing the hydrogen. So the zinc now forms an ionic linkage with the chloride, and the hydrogen is released by itself, and hydrogen is a diatomic molecule, so hydrogen is only found as H2 when it's produced. And this is, in this case, the H2 is actually a gas that is released. So the zinc chloride stays dissolved in the water, in the acidic water, but the H2 gas actually bubbles out. You can see this as bubbles. Bases will also react with a number of metals as well and produce hydrogen gas also, but these are much more complicated reactions beyond the scope of this course. Conductivity. Well, conductivity is really passing electricity through some chemical or some object. So if electricity can pass through very easily, we call that material conductive or a conductor. So anything that produces a lot of ions, charged particles, plus and minus particles, cations and anions, is a conductor. It has high conductivity. Well, strong acids what strong acid means is that this is an acid where when you put it in water, all of it splits into the H plus ion and whatever anion is left of that acid. 100% breaks apart. And that is what we call a strong acid, and it releases electrolytes, and since all of it becomes electrolytes, we would call a strong acid when it's in water a strong electrolyte, and therefore there are lots of ions, so this will definitely conduct electricity. Weak acids will not break apart so much. Only a tiny fraction will break apart, and they're very weak electrolytes and very poor at conducting electricity. The same is true with bases. Strong bases will break apart in water, produce lots of ions. Those ions are electrolytes and can conduct electricity. So strong acids and strong bases conduct electricity. Weak acids and weak bases don't really split into their ions very well, and there aren't many electrolytes, so those are weak electrolytes, and they are poor conductors of electricity. pH. pH is something we're going to talk about in another module in this unit, but pH is a measure of acidity. And there's a calculation associated with it, but the calculation has a negative sign in it. So what you find is that high acid becomes low pH. So low pH is anything under the number 7. Our pH scale at 25 degrees centigrade, about room temperature, our pH scale goes from 0 to 14. And the bottom half of that scale is acidic. Low pHs from 0 to 7 are acidic. High pHs above 7 to 14, are called basic or alkaline. Alkaline is another term. An acidic solution means there are lots of protons produced, which means there's a lot of hydronium ions, much more than the hydroxide ions that might be in the water. Whereas in a base solution, shown in blue here, the hydroxide ion concentration is increased, and it's much greater than the hydronium ion. And this will be true no matter what kind of base you put in water. Either the base will directly make hydroxide, or the base will indirectly produce hydroxide. So the base will always produce hydroxide. The acid will always produce this H3O plus hydronium ions. So if there's a lot of acid there, you're going to get a lot of hydronium, low pH. If there's a lot of base there, you're going to get a lot of hydroxide, high pH. Now the pH right in the middle, 7, is called neutral. Only 7, a pH of 7, right on 7, 7.0, 7.00, is called neutral. Anything lower, acid, anything higher, base. And we have a lot of different dyes, what we call indicator dyes or indicator compounds, that change color. Some change color with acids and bases, some change fluorescence, some change light-producing qualities. They're called chemoluminescers. So we have a lot of different chemicals that will change in one way or another if there's acid or base around. And the most famous of these, one of the earliest ever used, is a chemical called litmus. You may have heard of somebody saying the litmus test. And the litmus test means a chemical that is soaked into paper called litmus. You soak this dye into paper, and if you dip this paper into acids, the paper will turn red, and if you dip it into bases, the paper will turn blue. So at low pH, it will be red. At high pH, it will be blue. So let's look at acids and what they do in water. So we have the simplified version of a general acid, our HA, our theoretical acid, H bound to A. And this can release H plus ions, that's the acid part of the acid, and an anion of some type, A minus. And that will differ with every single acid. The A minus will be different in each case. And they're all dissolved in water, so they're all aqueous. And we have this generalized equilibrium. The acid can become the A minus, the anion, and the proton, and this can go backwards. Strong acids go all the way to the right. There's no coming back. Weak acids can go back and forth. In fact, most of it doesn't go at all. Most of it stays on the left side. But this is the equilibrium that we have. It goes back and forth. But the more proper way of showing this is that you're really reacting the acid with water, and the same will be true when you're doing this with bases. Acids react with water. If there's no other base there, the water will act as a base and pick up the proton directly, and you'll still produce this anion, A minus, that's dissolved in water, but you'll generate aqueous hydronium ions. So again, you have an acid and a base producing a conjugate base and a conjugate acid. And this is always going to be true in any acid-base reaction. They always come in pairs. So these are equilibrium expressions, meaning they can go back and forth. But if they're strong acids, they don't go back and forth. They just go forward, and that's it. Water, as I mentioned, can act like a weak base if there's no other base added to the acid. So water will form the hydronium shown above. And the example of that I've already shown you is HCl plus water makes hydronium ion, not just the free proton, and chloride, which is what's left over of your HCl, your hydrochloric acid. Another one would be sulfuric acid, which is another strong acid. Both of these are strong acids. And sulfuric acid can release 2 protons. It does it one at a time. I've shown the reaction where it releases both of the protons. So you need 2 waters to pick up the 2 protons. So each water will pick up a proton, becoming a hydronium ion. So we have 2 of those. And we release sulfate ion, which you already learned about when we were studying polyatomic ions. In fact, all of the polyatomic ions, if you add enough protons to them to get rid of their charge, all of the negatively charged polyatomic ions, if you add enough protons to them to get rid of their charge, you will make an acid. Sulfate will become sulfuric acid. Nitrate will become nitric acid. So base associations, okay, so now you have base reacting with the water. Now this base can be a hydroxide, it can be one of those nitrogen bases I showed you before, but they're going to react with water if there's no other acid present, because water can act as a weak acid as well as a weak base. And in this case, being a weak acid, the water will donate its proton to the base, a proton acceptor. So the proton is literally shifted from one to the other, and in this case, you're just moving the proton from the water to the base, forming the protonated base, BH+, And what's left of the water is a hydroxide ion, which is a strong base. So you'll notice in this reaction, no matter what base you throw in water, you're going to produce hydroxide ions in that water. Again, you have a base reacting with an acid. It's not a great acid. It's water, which is a very, very weak acid, but it does the job. And you end up producing the conjugate acid of the base, what we call the protonated base, BH+, and you produce the conjugate base of water, which is just water stripped of its H+. So you take away an H, you take away a plus, and you're left with OH and a minus sign, hydroxide, a strong base. Again, these are equilibrium reactions. They can go back and forth unless the base is a strong base, in which case this will only go forward and will not go backwards. So water acts like a weak acid when there's nothing else reacting with the bases. So water will form the hydroxide ion, which is a strong base. So no matter what base you throw in there, you're going to produce OH minus ions, strong bases. You may produce only a little bit if it's a weak base to start with, or a lot if it's a strong base to start with, but you'll produce hydroxide ion. So, for example, ammonium, a weak base. Ammonium is a weak base, but when it reacts with water, you produce NH4 plus ammonium and hydroxide, a strong base in this case. Now, this reaction, because ammonia, NH3, is a weak base, not much of this goes to the right side of the reaction, only a little bit, but you do produce some hydroxide, and you can see the solution that you end up with as being basic because of that hydroxide. Another example would be to take sodium hydroxide, a strong base, and put it in water. And this one's an interesting reaction because what happens is the NaOH splits up into, and I'm going to write this, actually I'll write this right below it here for a second. Na plus, the second it hits the water, it's going to completely split into Na plus and OH minus because sodium hydroxide is very soluble. And now you have this incredibly strong base reacting with this weak acid. Well, what happens? Well, this strong base steals a proton from the water, and you end up making this hydroxide becomes water, but what happens to the water? It becomes hydroxide, that OH minus ion. So here's a reaction where you start with a compound, two compounds, and you end up with the same compounds, but they are made from different parts of the other molecules. If I was able to label one of these oxygens, if I say used an isotope of oxygen, I used O18 for this oxygen here, we would find the O18 in the water in the product because this OH minus became this water. Now, you don't have to worry about these isotope type experiments, but these are the kinds of experiments that scientists use to trace elements as they move through chemical reactions. Another example would be KOH, potassium hydroxide, a strong base, and now I'm going to add an acid, hydrochloric acid, HCl. And you'll notice we get this reaction of producing, whenever you have a hydroxide base and a proton-releasing acid, you're going to end up with a salt. In this case, our salt is potassium chloride, and you're going to end up with water because the H plus is bound to the OH from the base. We have the OH minus here, we have the H plus here, and it's a double replacement reaction in this case. So anytime you see a proton and a hydroxide being mixed together, you're going to get a double replacement reaction where you're going to end up with a salt of some type. Salt just means ionic compound, and water as your products. So now let's look at some reactions of acids and bases. You've already seen a few, and you've seen a couple of these reactions in previous units of this course, but let's talk about the different types. Acids, as you know, can react with bases, and we actually call these interactions neutralizations. We're neutralizing the acid with the base, or we're neutralizing the base with the acid. And these reactions come in a couple different varieties. Some are double replacement reactions, the ones with hydroxide bases, and they're single replacement reactions with the non-hydroxide bases. So let's look at a few of these. We've already talked about HCl and NaOH producing NaCl, our salt, and water. We can also have another one where we're having two nitric acids. HNO3 is nitric acid, and we react two of these with magnesium hydroxide. So this is another strong base, and they will end up producing a salt. In this case, the salt is magnesium nitrate and water. And because we started with two protons on the left, and I'll just underline those, two protons here and two hydroxides, we're going to end up with two waters as our products. We can also do other acids and other hydroxide bases. Here's sulfuric acid and calcium hydroxide to produce calcium sulfate. The calcium ions find the sulfate ions and they form an ionic compound, a salt, calcium sulfate. And because we started with two protons and two hydroxides, we're going to end up with two waters, again in this. So in each of these cases, with a proton-releasing acid and a hydroxide type base, we're going to form some kind of salt and water. And this is very hot reactions. They're very, what we call exothermic. They produce a lot of heat, so you have to be careful with these. But if we react an acid with a non-hydroxide base, say something like ammonia, ammonia will remove the proton from the acid and form ammonium, NH4+, and leaving behind the Cl- from the acid. So you'll notice we end up with two ions here, a cation and an anion, and in fact, if you dried out the water from this, this would actually form an ionic compound. Remember, that's an ion, though we don't usually write the ions when we write it as a compound. I'm just showing you how they come together, and this is called ammonium chloride. Well, in this case, the ammonium chloride is just produced by reaction with the acid and the base, and you really will only end up with one product if you dried this down, a single salt. Now, you'll notice what's happening in this reaction is that the proton is moving over to the ammonia. So what that means is that the ammonia, which is our base, is swapping places with our chloride, which is a terrible base, but it's a base nonetheless. Because both of them can, in theory, pick up a proton, so they're both bases. So the chloride and the ammonia swap places. So this is a single replacement reaction, whereas all of these three are double replacement reactions. You're swapping anions completely. So I'll erase that right there. Okay. We also know from past experience when we were looking at chemical reactions, especially the single replacement reactions, that many metals are reactive enough to react with acids like hydrochloric acid or other acids. We know that metals like zinc and calcium and magnesium are quite reactive with acids and will produce a metal salt. Again, we get the salt. But in this case, what's left over is our hydrogen gas, because we have hydrogen ions, which will become, two of them will come together and form H2 gas. Why is that the case? Well, that H2 gas, the H2, is the natural elemental form of hydrogen, so you can't just leave an H behind. You have to leave H2 because that's the form you find the element hydrogen in, H2 gas. And this would be true, I could write this for any number of other metals as well that react with acids, like sulfuric acid reacting with magnesium, another very reactive metal. Now we have a different acid, so we make a different salt, magnesium sulfate. And again, the hydrogen is released as hydrogen gas. And we have a new set of reactions that you haven't seen before. Acids can react with metal oxides. Metal oxides you can think of as kind of disguised versions of metal hydroxides. In fact, many metal oxides, the second you put them in water, will become metal hydroxides. They're that reactive. So here's a metal oxide, magnesium oxide, and in this case, you actually have two of these HCl's will react with the magnesium oxide to produce one magnesium chloride salt and one water. We have enough protons, two protons and one oxide to make our H2O. So it's a different reaction than you've seen before. So just be aware of this kind of reaction. But the important ones are the first two up here. You should also know that acids can react with carbonates and bicarbonates. Bicarbonate is the old name, but the more common name of hydrogen carbonate compounds. So these are compounds, these are ionic compounds that have CO3 minus 2 in them, carbonate, or HCO3 minus 1, hydrogen carbonate, otherwise known as bicarbonate. So this first reaction is a carbonate compound reacting with acid. Our hydrochloric acid, HCl, is reacting with calcium carbonate, and we will still get a double replacement reaction. The calcium will bind to the chloride to make calcium chloride salt, and the other product will be the H pluses from the acid reacting with the carbonate from the calcium carbonate to make this new acid called carbonic acid. But carbonic acid in water at most pHs, at low pHs or neutral pHs, does not stay this way. It's a very unstable molecule, and this will immediately break up in a second decomposition. So we actually have a double replacement here, and this reaction of going to here, I just carried over the calcium chloride. It's the same thing, nothing happened to it. This is actually a decomposition reaction. So you end up with two reactions, one right after the other, because this molecule is relatively unstable, and a lot of it will split, and we'll end up producing water, which just stays there, you don't see it, and CO2 gas, which is coming off. Now you will notice we are taking carbonic acid and turning it into water and CO2. And you were told during our chemical reactions unit that combustion reactions of carbon compounds will produce water and CO2. But this is not a combustion reaction. This is the exception. This is why when you look for a combustion reaction, your starting material has to react with oxygen gas. This is not reacting with oxygen gas. The carbonic acid is merely decomposing into two more stable molecules, water, H2O, and carbon dioxide, CO2. Another version of this reaction is to start with a bicarbonate, or the hydrogen carbonate. So now we have HCl again, and we're reacting it with sodium bicarbonate, or sodium hydrogen carbonate, shown here on the left. This is actually baking soda that you can buy in the store. That's what the bulk of sodium, that's what baking soda is. It's sodium bicarbonate. And it will react with acid. In this case, you only need one acid, and you'll produce a salt. Since we started with sodium and we have chloride from our acid, we'll end up with sodium chloride instead of calcium chloride this time, because we started with calcium salt before. And we'll still end up making a carbonic acid. Now, the NaCl, nothing happens to it again. I'm just carrying it over. But the carbonic acid can again decompose into water and carbon dioxide gas. And these are the reactions you should be familiar with, and we'll stop here.